Hello, my name is Robert Hazen, and it's going to be my great pleasure to share with you the great principles of science in this 60-lecture series. This series is an outgrowth of work that Jim Treffel and I have put together at George Mason University in Fairfax, Virginia, where we're both Robinson Professors of Science. We developed a variety of courses in scientific literacy, in science and society, and the way science interacts with arts and scientific ethics. I'm also a research scientist at the Carnegie Institution of Washington's Geophysical Laboratory, and there I do research on materials at high pressure. I'm interested in the nature of the Earth's deep interior, and also an exciting new project on the possible origin of life in deep ocean hydrothermal systems. And throughout the course of lectures, I'll be telling you something about that research, as well as the research of many other individuals. My passion as a teacher is to share with you the incredible stories, the incredible adventure of scientific discovery. I want to tell you about the mind-boggling insights, the mind-bending discoveries, the transforming nature of science in the modern world. Science is the greatest ongoing adventure of the human condition, and you can share in that adventure. In this first lecture, I'm going to ask you a question. How do you know what you know? Humans have devised many different ways of knowing. They have religion, philosophy, the arts, and science. They all help us to understand our place in the world. But of these varied pursuits, science holds a special place as a method designed to ask and answer questions about the tangible aspects of the physical world. Indeed, the great principle for this first lecture is that science is a way of knowing about the natural world based on reproducible observations and experiments. In this series of lecture on the great principles of science, we're going to explore the full range of the physical and life sciences, including topics that are traditionally part of physics and chemistry, geology, astronomy, and biology. We're going to find that these disciplines share a common methodology, and that in fact nature knows none of these disciplinary boundaries that we as humans impose on it. Throughout this series, we're going to see that sciences are linked by this methodology and a common set of natural laws. My three objectives in the introductory lecture are first to describe briefly the nature of science as a way of knowing. Second, I want to explain the philosophy of this unusual integrated science course, a course probably quite different from any that you've ever taken. And third, to look briefly at the social structure of modern science as a human endeavor. Science is a way of knowing. It's based on reproducible observations. It's based on controlled experiments and on theoretical reasoning rooted in mathematics. One of the most simple and elegant definitions of science is that it's the search for laws that describe the organization and evolution of the universe. Science is fundamentally different from other ways of knowing because it's based on independently verifiable facts. Facts about physical phenomenon. It strives for consensus on the basis of those facts. I have a wonderful pleasure of participating in a team-taught course on visual thinking. It's taught by an artist, by a psychologist, and myself, a scientist. And we often begin that course by telling the story of three umpires. The scene is in a bar after a game, and three umpires are discussing how they call balls and strikes. These three guys all have day jobs, by the way. One of them is an artist, and he says to his friends, "I calls them as I sees them." The other two nod, but the second one says, "Well, it's a little bit different for me. I'm a scientist. I calls them as they really are." The third umpire shakes his head. He says, "Nope, they ain't nothing till I calls them." He's the psychologist. The point is that there are many different ways of knowing. If science is a way of knowing based on reproducible observations, experiments, and mathematical reasoning, then think how it differs from the other ways of knowing. The arts, the philosophy, religion, and so forth. Science differs from religion in which truth is revealed by sacred text and by other sources. Truth is accepted on faith. If you are a true believer, there is no observation you can make that will supersede that faith. Science also differs from the arts, in which truth is explored through each individual's unique vision. Each artist sees the world differently. I want to tell you a story about Pablo Picasso, who, the story goes, was riding on a train in France. This was after World War II when Picasso was very famous. And one of the fellow passengers in the train noticed Picasso sitting there and realized this was one of the great contemporary artists. He started grumbling and said, "Contemporary art, modern art, it's terrible. Who could possibly look at that stuff? It bears no relationship whatsoever to reality. It's just not real." Picasso overheard and said, "Well, what is it you don't like about art?" He says, "It doesn't look like anything. It's not reality." And Picasso, sort of taken aback, said, "Well, what's reality? What looks like reality?" The gentleman thought for a while, pulled out his wallet and said, here's a photograph of my wife. This picture looks exactly like her. It's really like her." So Picasso pauses and looks at the photograph. Well, she's awfully small and flat. So the artist's vision is unique and quite different from those of the scientist. Science also differs from political science and from social science. In science, the ultimate goal is to reach a consensus based on reproducible and verifiable facts. But in politics, in history, in sociology, and so forth, there are many equally valid interpretations of events, many different plausible policies, for example, for the government. The richness of these disciplines results from a multiplicity of interpretations of past and future events. So again, it differs from science. Science also differs quite profoundly from pseudoscience, things like astrology, psychic phenomenon, UFOs, for example. These aren't based on reproducible and independently verifiable observations. A key point here is that most scientists don't reject the existence of UFOs absolutely. They don't say that psychic phenomena are impossible. But it's just that the reports of these phenomena are invariably anecdotal. That is, they're not subject to independent observations. You can't test them, you can't verify them. And so they're outside the domain of science. If and when reproducible observations become available, if, for example, we actually have a fragment of a UFO and it can be studied in a laboratory, then that subject will satisfy the grounds of science, and suddenly you have a subject that becomes scientific even though it wasn't before. The process of science provides a powerful tool for observing the world, for learning about how it works, for making predictions about future events, and also for discovering ways to modify our environment. I want you to imagine yourself in a society without science. Imagine yourself, for example, back 4,000 years to a primitive agricultural community. What you'd notice first, I think, is a fundamental difference in our material well-being. You'd lose technologies associated with health, food, communications, transportation, housing. You'd notice those things immediately. But I think you'd also notice something else. You'd notice a more subtle but equally profound difference in logic systems. The belief, for example, in a predictable universe. The understanding of cause and effect, which is so much part of our lives and our thinking. As we go through this 60-lecture survey, I hope that the unique character and power of science becomes clear. Before I go on, I owe you an explanation. Why is this course organized in this non-traditional way, in this integrated way? Jim Treffel and I developed this course on the great principles of science in the early 1990s, and it was in response to a growing call for scientific literacy for all Americans. In support of this course, we wrote a textbook called The Sciences: An Integrated Approach. This makes an excellent companion volume for the course. It does follow more or less lecture by lecture what's in this course, although my lectures are going to expand on many of the topics which are included in the book. We've now been teaching that course for 10 years, and many of the students find that it changes, it transforms the way they think about science. Indeed, most of our students are non-science majors, but they get a richer understanding of the role in science in their everyday lives. In the modern world, every citizen needs to be scientifically literate. If you pick up any issue of any major newspaper any day of the week, you're going to find stories. Just this morning's Washington Post, and whenever I do this demonstration, I always use that day's paper to be fair. You'll see dozens of stories. The first page, you always can start with the weather. That certainly is a story related to science. But here, on the bottom of the page, there's a story about the Brooklyn Bridge crumbling because the materials of which it's made are gradually deteriorating. In this course, we'll talk about the properties of materials, what makes them strong or what makes them break. The second page, jury awards ex-smoker $50+ million. Well, what's the nature of smoking? Why is it dangerous? What causes cancer? The next article, Navy fails to ignite leaking cargo ship, an article on the environment. And you'll see article after article in the environment and on global climate. The next page, 3 articles on various medical findings about breast tissue, about red cells, about sciatica, and on it goes. In the business section, in the sports section, every section of the paper, you're going to find articles that relate in one way or another to our bodies, or the materials in our lives, or the economic implications of technological discoveries. There are 4 principal reasons that people cite for the importance of scientific literacy, which to me is the ability to read the newspaper in all its richness with scientific content. The first of these is that scientific literacy helps consumers make informed decisions. Science content provides a basis for understanding why products work. The scientific process of inquiry helps you make critical thinking decisions. You have to make personal choices about health care, about the various drugs that you're going to consume, about the various treatments that are offered to you. You need to make informed decisions about diet and nutrition. Science helps you here. You need to worry about environmental issues. What kind of detergents are you going to use? What kind of automobile will you drive? What about the lawn care and how does that affect the environment? Scientific literacy helps you make those decisions as consumers. A second reason for scientific literacy is that it's important in many jobs. Many modern jobs depend on science, either directly or indirectly, as well as technologies that are developed from scientific discoveries. Doctors, of course, and of course their patients, need to understand the benefits and risks of all sorts of diagnostic procedures, things like X-rays and MRIs. What do they do to your body? What's the technology behind them? You need to understand drugs and other sorts of treatments. If you're a lawyer, you need to understand an expanding arsenal of forensic techniques that are based on things like genetic fingerprinting and spectroscopic analysis, drug testing, and so forth. If you're in business, if you're an investor, you need to understand the nature of modern high-tech stocks, companies in genetic research, in the semiconductor industry, in drug development, and so forth. And if you're in politics, if you're a legislator, you're going to have to vote on issues such as funding for science, as well as new laws, laws relating to medicine, laws relating to the environment. Those all require an understanding of the principles of science. All right, the third reason to promote scientific literacy is our children. Scientific literacy in you provides a foundation for teaching our children about their natural world. Parents and teachers who are scientifically literate can reinforce a child's natural curiosity. You can explore the natural world together if you have that confident basis of how the world works. And finally, and my favorite reason, is that scientific literacy allows a person to share the richness of humanity's greatest ongoing adventure. This is an adventure of discovery and exploration that goes on day by day. Every day, scientists are discovering and sharing new things that we never knew before. And you can share in that adventure. I believe that everyone can achieve scientific literacy. The great principles of science can be presented without relying on complex vocabulary, on mathematical abstraction. We all live in a physical world of matter and energy, of forces and motion. Daily life is therefore an experiment, day by day, in that physical world. And you've learned to deal with the natural world in these ways. You have a wealth of experience on which to build your scientific understanding. In spite of this fact, there have been several definitions of scientific literacy that have confused this issue. I just want to digress for a second and tell you about those. I think scientific literacy is quite different from technological literacy. Sometimes you say to a person, "Are you scientifically literate?" And they say, "Oh, I can't even program my VCR." Well, programming your VCR is an aspect of technological literacy, as is using computers and other modern technical sorts of equipment. It's important, but it's not what I'm talking about with scientific literacy. Another way of confusing the issues is when you ask scientists about scientific literacy, and they seem to imply that scientific literacy means the people who are going into science as science majors. Oh, people keep dropping out of science. We just don't have enough scientific literacy. But I'm not worried about the 1% of people who are going to become scientists. I'm worried about the 99% who are not. That's who we need in our society to be scientifically literate. The realization of this need for all Americans to be scientifically literate has led to a new document, an extraordinary document called the National Science Education Standards. This document represents a strong consensus of thousands upon thousands of teachers, parents, administrators, and scientists who have gotten together to define what is the building code for scientific curriculum for grades K through 12 in the United States. Scientific literacy, according to this document, is based on a few overarching principles rather than extensive vocabulary and factual information to be memorized. These principles come from all the branches of science, from physics and chemistry, from earth sciences, from biology. Scientific literacy is also based on understanding scientific method. This is a process of inquiry that we're going to talk about extensively in the next lecture. It's the way questions about the natural world are asked and then answered. For those of you who are teachers or are parents, I've provided a concordance to the National Science Education Standards in your booklets. And this will help you because every major content standards in the National Science Education Standards is also covered in this lecture series. And you can go from the standards then to the appropriate lecture for that particular standard. The principal objective of this course is to introduce the great principles of science, to explore how scientists discovered these sweeping ideas, to show how great principles come into play in our lives in often surprising and in wonderful ways. These lectures are going to attempt to integrate all the sciences, unlike the traditional division of science into physics and chemistry, biology, making them separate departments. This division of scientific disciplines is insidious, and it's a relatively recent phenomenon. It's in large measure, I'm told, the result of the structure of European universities in the 19th century. In European universities, each department could have one professor. So if you had a science department, you have one professor of science. But as science has expanded and it got more complex, many distinguished people arose, and so you had to develop new departments so that each of these distinguished individuals would have his or her own department. As a result, they became a proliferation of departments. It got to ridiculous extremes. At Cambridge University in England, there were 7 different departments of chemistry for colloidal chemistry and physical chemistry and polymer chemistry because you had 7 distinguished people who had to have professorships. That's an artificial division. It has nothing to do with the natural world. Typical newspaper stories will demonstrate what I mean by this. Just look, for example, at the recent stories that have appeared about radioactive waste disposal. Well, what department is concerned about radioactive waste disposal? Certainly physics, because radioactivity is a physical phenomenon. And then the chemists have their say, because radioactive isotopes are chemicals and they interact chemically with the environment. Geologists are concerned because you have to bury these chemicals someplace in the earth, so you have to know something about the earth. And of course, biologists have their say because we're biological systems who are affected by radioactivity. So what's nuclear waste disposal? Is it physics? Is it chemistry? Is it biology? No, it's all of the above, as are virtually every story you're going to read about in the paper. That's the nature of the scientific issues confronting us. For the final third of this lecture, I want to examine the social framework for scientific enterprise. Science is a human endeavor. It has its own distinctive organizational structures, just like any human endeavor. Right now, there are on the order of 350,000 scientists who work in the United States. Primarily, they work in government, in industry, and in academia. The 1999 U.S. government budget allocates $78.2 billion for research. That's your tax dollars at work. Now, slightly more of that money, more than half of that money, is for defense-related projects. And of the civilian part of that budget, most of it goes for R&D at the National Institutes of Health, which is in Bethesda, Washington, Bethesda, Maryland. You have the National Science Foundation. You have NASA, the big space program, and then also the Energy Department and the Commerce Department. They consume most of the civilian research budget. The Washington-based American Association for the Advancement of Science is the largest general science society in the United States. It has about 130,000 members. It's the major society representing all the different branches of science, and it publishes a wonderful weekly journal called Science, which includes forefront advances in science in all the different disciplines. It's one of the few scientific periodicals that comes out weekly and contains articles from all the different branches of science. We also have in Washington, D.C., the National Academy of Sciences. This is an organization that was founded originally by President Lincoln in the 1860s, and it's designed to advise Congress on a whole variety of issues in science and technology, and indeed they publish a monthly journal called Issues in Science and Technology, which does exactly that. When you see government policies on the environment or on health, on agriculture and so forth, often these policies will be informed by the National Academy of Science. The rigid division of science into separate departments may have hindered scientific literacy of non-scientists, but I have to admit that there is a certain rationale underlying this structure. I want to tell you about these four divisions of physics, chemistry, biology, earth science. And you can see how they differ from each other, even though they do share common principles and even though the methodology is the same. Physics. Physics has to be placed first in the hierarchy because the laws of physics have to apply to every natural system. Whether it's large or small, whether it's living or non-living, the laws of physics apply. Physics can be defined as the study of matter in motion, or more abstractly, how particles interact. An understanding of the great principles of physics must precede the treatment of chemistry or geology or biology, because those are more specific systems looking at atoms or planets or living things. Physics applies to everything. Classical physics deals with everyday phenomena of matter, of energy, forces, and motion, and we'll look at all of those ideas. Great principles associated with these concepts include Newton's laws of motion, the law of gravity, the laws of energy and heat, which are called thermodynamics, and the laws describing electricity and magnetism. These principles operate every day. They operate in everything that you do. Life, therefore, is a terrific physics laboratory. Then we have modern physics, which deals with realms beyond our daily experience. Very, very small objects, very massive objects, very fast objects near the speed of light. And these require new physical laws. These are codified in the fields of quantum mechanics, nuclear physics, particle physics, and relativity. And I'll be touching on all of those subjects as well in the coming lectures. Most of the 50,000 or so physicists in North America belong to the American Physical Society. This group is part of a much larger umbrella organization called the American Institute of Physics, based in Maryland. This American Institute of Physics has about 100,000 members, including geophysicists, astrophysicists, scientists in other related fields, and they publish a wonderful monthly journal called Physics Today, which is available on many newsstands. So it's accessible to the general public as well as to the specialized people in that field. Now we come to chemistry. Chemistry is the study of atomic interactions, especially the study of chemical reactions and the formation of new materials. Some scientists view chemistry as a specialized subdivision of physics, but it really has developed its own goals and its own culture. Modern chemistry is rooted in the alchemical sciences of the Middle Ages. It's an empirical science. Inspired guesswork often leads to great advances. It basically involves mixing new chemicals together in new ways and seeing what happens. And once in a while you get a new material that really benefits society in a variety of ways. Chemical research and chemical engineering are very closely linked. It's often possible to scale up a laboratory benchtop experiment in just a few months to a full-scale manufacturing operation. Therefore, most chemists and chemical engineers together belong to the American Chemical Society, which is one of the world's largest scientific societies. Its 150,000 members receive the weekly magazine Chemical and Engineering News, which gives information both on the science and on the industrial aspects of chemistry. Then we come to my own discipline, earth science, my favorite science. It's the study of the origin, the present state, the dynamic processes in the earth, as well as other nearby planets, because other planets shed light on how the earth behaves. Unlike physics and chemistry, earth science deals with a large, complex system that has a distinctive history. So earth science is the first of the historical sciences, where you have to look to the past. Earth science is a relatively young field. It grew up out of the practical experience of mining, perhaps about 200 years ago. Virtually every material object you use is made from earth materials, materials obtained from the earth, whether it be the rock or the water or the atmosphere. Geology is the specific study of the rocks and soils and their distribution. Most geologists belong to the Geological Society of America or the American Association of Petroleum Geologists. Both of these societies have about 20,000 members. They have lots of publications. They have annual meetings and so forth. The Geological Society of America is based in Boulder, Colorado. I've always liked that. Geologists based in Boulder, right in the foothills of the Rockies. They're not in Washington, D.C. They're out where the action is, where the rocks are. The government supports the United States Geological Survey, which is, it monitors natural resources, it looks at water supplies. The government also supports the National Oceanic and Atmospheric Administration, which does the weather. There's another aspect of earth science too, that's called geophysics. That's the study of the Earth's dynamic processes, such as tides and hurricanes and earthquakes. And we have the American Geophysical Union with about 25,000 members. And it has, therefore, a much larger society because it has sections for oceanography and meteorology, as well as solid earth geophysics. And they too have their regular publication called EOS, and they have annual meetings and so forth of earth scientists coming from all over the world. And finally, we have biology, the study of living systems. These are by far the most complex objects we know, living systems. Because of its importance to health, to medicine, to biology, this is by far the best funded of sciences, and by far the most scientists are biologists. It's an extremely diverse discipline because there are so many different ways to study living things. You have, for example, botanists and zoologists, microbiologists that are concerned primarily with identifying the characteristics of individual new species. You have other biologists that focus on the dynamic processes, including things like evolution or development of an entire organism from a single fertilized egg, or genetic characteristics. Biologists can focus on life at many different scales, at the molecular level, inside a cell, in the ecosystem range, of whole groups of organisms together, or any place in between. The most obvious applications of biology are in health and medicine, and the government spends a lot of money on this with the National Institutes of Health in Bethesda, Maryland. It has an annual research budget close to $15 billion, and much of that money goes to grants for individual researchers around the country who are studying specific medical problems or just more general biological research for basic research purposes. Let me summarize this first lecture. We've seen that science is a way of knowing about the natural world. It relies on reproducible observations and experiment, on theoretical reasoning based on mathematical logic. It differs from other ways of knowing. It differs from religion, art, philosophy, from the social sciences, and from the pseudosciences. Scientific literacy, the content of this course, encompasses those facts and concepts, history, methodologies that you need to understand the scientific issues and to follow the great ongoing adventure of scientific discovery as reported in the news. Finally, we saw that science is conveniently divided into several disciplines: physics, chemistry, earth science, and biology. Nevertheless, all scientists use exactly the same methodology. This is called the scientific method, and that is the subject of the next lecture.